So maybe we can slowly start. Hello, everyone. It's my great pleasure to introduce today Antonio. So thanks, Antonio, first of all, for taking the time to present to us today. So Antonio is a faculty member at USC in California, and he has been there since 1994 with an extensive experience of supervising PhD students and doing research in the wider domain of signal processing, more recently graph signal processing, machine learning, multimedia compression, and wireless sensor networks. He's very involved also in different IEEE activities. His research has been also awarded with many awards, one of them also including graphs that is in IEEE Signal Processing Society. And finally, also thanks to Antonio, we have a book on graph signal processing, which we are looking forward to read. So today he will talk about the very important problem of graph construction for machine learning. So I think till now, all the talks that we had, they were mainly focused on network data or graphs that were already given by the application domain. So today, I'm assuming that the topic of the talk is about how to get a good graph for different machine learning applications. So Antonio, I will give you the floor, and thanks again for your time.
Great, thanks, Dorina. It's very nice to be here, and thanks for the invitation once again. And more about the book at the end, but yeah, I'm the first one who's very happy that it's coming out finally after a very long process. So today I'm going to focus on graph constructions and how graphs can be used in a number of machine learning applications. I first want to acknowledge that this is work primarily with my students, two former students, actually, and Amir, and a current student, Sarat, whose work is most of what I will be presenting today, along with collaborators at USC, Romain Constantino, Salman Avestimer, and Marti Soltanul-Ketlabi. And other collaborators have contributed to different parts of this work. And most of my work is funded by NSF through a series of grants. And also some of this work is funded by a DARPA grant. All right, so let me start with a bit of motivation to make the case that graphs are useful for applications where we're considering data. And so throughout this talk, I'm going to consider a scenario where I have data, I have a data set, could be a training or testing data set, and I'm going to look at one data sample at a time. Initially, these data samples are not structured, they're located in some feature space, but I'm going to construct similarity graphs for these data sets, right? So I'm going to connect data points, samples to each other based on proximity. And then a conventional way to do this is to define a distance between two samples. So you take x1, xi, xj, and based on the distance, you define a weight where the weight decreases as the distance increases, right? So two samples that are close together will be connected by an edge in the graph. The edge will have a large weight, which corresponds to high similarity. Two nodes that are far away in the graph or corresponding to samples that are far away will have a low weight, or potentially they will not be connected, right? So I'll talk about both how to go from this data to a graph construction, talk about good ways of constructing graphs, and then talk about how to use these in both applications that have been considered in the past, such as active semi-supervised learning, and also in more recent work where we're looking at using these methods to understand deep neural networks. So that's the general idea. Now, this work is based on graph signal processing. I'll make the connection in a few minutes, but just to make clear, in this context where we have data points, the labels are what we consider the signal, right? So here a graph signal would be the label data. For example, if you have a data set with images of cats and dogs, the cats will have a label 1, the dogs will have a label -1, right? So this assignment of a label to data corresponds to the graph signal. Okay, so this is mostly what I would just said. I'm going to start with some very basic concepts in graph signal processing that will be useful in the rest of the talk. I'll keep it pretty basic, and then we'll talk about graph signal sampling and its connection to semi-supervised learning. Then I'll talk about graph construction and a graph construction method that we've proposed. And then I'll discuss applications in the context of deep neural networks. Okay, so that's the plan for today. Basic definitions: a graph contains vertices and nodes. They're connected by vertices or nodes and connected by edges. I'm going to define a graph with a set of vertices. The edges will be weighted, so the connections between two nodes will be weighted. And as is done in graph signal processing, and before that in spectral graph theory, we define the adjacency matrix that contains the edge weights and has a number of entries that is equal to its of size number of nodes squared, right? So each entry corresponds to an edge weight. The degree is the total sum of edges that are weights of edges that arrive at one particular node. And we will use the graph Laplacian matrix, degree minus adjacency. And as I mentioned earlier, if we have n nodes, the graph signal consists of the scalar or vector values that are associated with each of those nodes. Okay. All right. So the work that I'm going to present, and indeed much of the work in graph signal processing, builds heavily on spectral graph theory. So if we start with the combinatorial Laplacian that I just introduced, degree minus adjacency. For undirected graphs, this is a positive semi-definite matrix. I'm going to focus on this operator, but there could be others, such as the normalized Laplacian, that could be used instead. Okay, so we perform a eigendecomposition of this matrix. These eigenvectors are orthogonal, and these are the frequency modes for the graph. And the corresponding eigenvalues are all non-negative and real, and those correspond to the elementary frequencies. Okay, so in the context of graph signal processing, the eigenpair system, the pairs of eigenvalues and eigenvectors, that provides a Fourier-like interpretation, and that's what people in this field call the graph Fourier transform. Okay, why is this a reasonable thing to do? If you go back to the combinatorial Laplacian, we can define a graph signal variation. Okay, so graph signal variation for any vector u is going to be the Laplacian quadratic form, and this will be the sum of values of the vector u at nodes I and j, weighted by square of this difference, weighted by the weight between I and j. Right now, you can see that if this is the same between two pairs of nodes, it will count more if the weight is larger, right? So what counts more towards variation is the difference in values between nodes that are close, that are similar, okay? And then if you take this definition of graph signal variation, then the eigenvector decomposition can be interpreted with the Rayleigh quotient, where the kth eigenvalue corresponds to a vector that is orthogonal to the first k-1 eigenvectors, and that minimizes this Rayleigh quotient, where you see that what it does is it minimizes a normalized graph signal variation, right? So basically, when you construct these eigendecomposition, you're starting with the first eigenvector, which can be seen to be 1 for the non-combinatorial Laplacian, so a constant signal throughout the graph. Then this corresponds to eigenvalue 0, and then successive eigenvalues have higher variation, right? And therefore higher graph signal variation. And so what we have here is that these orthogonal eigenvectors, the eigendecomposition, are ordered by increasing graph signal variation. All right, how does this look in practice? You may have the toy graph that I showed before, and the first eigenvector is a constant, all ones, with eigenvalue 0. As I increase the eigenvalue, 0.04, 0.20, and so forth, you observe more changes in the signal in the graph, right? So the first signal is all constant, then you have that all of these values are positive, all of these are negative, but there's only one region where there's transition from positive to negative. And if you go to the highest eigenvalue, you can see that there's a lot of variation, changes from positive to negative from node to node. Okay, so the basic idea that I will return to throughout the talk is that this notion of graph signal variation, where increasing eigenvalues correspond to more variation of the signal in the graph. Okay. All right, so now let me jump into what was also for me the first foray into analyzing learning systems from a graph perspective, and in particular from a graph signal perspective, and this was the problem of semi-supervised learning. And in semi-supervised learning, we made the connection with graph signal sampling. Okay, so graph signal sampling is analogous to the sampling problem in conventional signal processing. So we have a graph with values, signals at each of the nodes, right? And for various reasons, we would like to observe only part of the graph and then interpolate to other nodes in the graph, right? So we want to measure a few nodes to estimate information, and then we want to reconstruct the signal throughout the graph. Okay, so we start with a complete graph. Now we select the set of nodes that we observe. This is the set S, and then from this observation only, we reconstruct the signal in the whole graph. That's the idea of sampling. And we need to define a notion of frequency, because unless the signal is band limited or smooth in some way, we won't be able to reconstruct, right? So in general, if the signal is completely arbitrary, we cannot recover it. But if the signal is sufficiently smooth, we will be able to recover it. How do we select the sampling set? This is one of the most difficult problems in this context, because there's no obvious way of doing regular sampling, right? We cannot start by selecting every other node. So we have to define a set that is best for sampling and then observe signals there. And for reconstruction, we need filtering. And there's a lot of work that has been done in defining graph filters. Okay, so this is the problem of graph signal sampling. How is this related to semi-supervised learning? Well, there are lots of methods that are being proposed for graph signal sampling. I'm not going to go into any of them in real detail, and I recommend an overview paper that was recently published in Signal Processing magazine that covers a lot of the recent work. The algorithms have different flavors, they have different complexity, different requirements, and so on. But let me not go into that. Okay, what is the problem of active semi-supervised learning? Well, remember the example of the data set that I gave at the beginning, right? It's structured data. Initially, you may not have labels, but you may have lots of data. So the unlabeled data is fairly abundant, but labeled data is expensive and scarce, right? So labeling is what's really expensive. And it has been shown that there's better performance if one uses some labeled data, then does label propagation to unlabeled data, and then trains. Okay, so the questions that are relevant in semi-supervised learning are predicting unknown labels from known labels, right? So partially supervise the data set and then use methods to estimate labels at other locations. And this label propagation problem can be addressed from a perspective of graph filtering, right? You have observations in some nodes, you filter them to have a smooth interpolation in other nodes. The second problem is the active learning problem, where we want to decide what to label, right? And if we start with unstructured data, we could randomly select some data points, data samples to label, but we want to optimize that. And the active learning problem, we argue, is basically a sampling set selection, right? You decide what to observe, get the labels in those points, and then generate the interpolated labels in other locations. Okay, so that's exactly what we did. We start with a data set without labels. The data points are nodes. The edge weights are based on similarity. And again, I'll talk more about the construction and various flavors of constructions a bit later. And then what we're going to do is sample some of the data points, right? So in this example, I constructed a graph with nodes. I created the edge weights, and I will be observing only these two values and then interpolating to the others. So these class indicator vectors are graph signals for which we have some observations, right? So in this example, we have two classes, red and blue, and we have two observations, one red and one blue. And these are labels that we want to propagate in a way that is consistent with the known labels and smooth on the graph, right? So it's kind of a low-pass filtering that you would use in signal processing. And so the question is, why does this work, right? I mean, it sounded like an intuitive idea to explore, but why does this work? So from a graph signal processing perspective, what we can do is look at the graph signal variation of the label signal, right? And in these plots, what I have is for three data sets, USPS, isolate, news groups. So one is small images of digits. The other is short speech utterances. The last one is text. For each of them, what we plotted is the cumulative energy of the label signals in the graph Fourier transform domain, right? So this is the eigenvalue index, right? From that corresponds to the number of nodes in that data set. And then this is the cumulative energy, right? So the transform is orthogonal. So in the end, the cumulative energy is all the energy goes through it. So you have one at the end. If the energy was randomly distributed through all the frequencies, we will have basically a diagonal line, right? And what you can see here is that for some data sets, with about 10% of the points, we would get 90% of the energy, right? So these data sets, for these data sets in particular, the graph signal variation of the label signals is low, which means that they're relatively smooth, right? And so in this representation, if you have some observations and you do label propagation, you will tend to propagate a label from one node to a neighboring node so that they have a similar label, and that works fairly well. Now, if this is the worst case, where the energy is completely randomly distributed across all the frequencies, you can see that this has a lot of energy in the low frequencies, this has less, and this has even less, right? And indeed, these three examples correspond to tasks that are increasingly difficult, right? And so the USPS classification is much easier than this one, right? And so what we can say also, and this will come back to towards the end of the talk, is that if we look at the graph signal variation of the label of a complex task, the signal variation will be greater than that for a simple task, right? And remember, that's because the graph signal variation measures the differences between signals, right? And in this case, those are labels at neighboring nodes, right? So if a task has big differences between neighboring nodes, it will be difficult. If a task has small differences between neighboring nodes, it will be easy, right? Okay, so now what we did, this is a fairly old paper by now at KDD, was we started with input data, constructed a graph. We applied a graph signal sampling technique that to do sampling set selection, and then we observe labels for the sampling, the nodes in the sampling set, and then we perform a reconstruction. Okay, so I'm not going to go into the details what we did, but generally for all the three tasks that I just mentioned, our method provides the best performance, right? It gives us the best semi-supervised learning performance. And as I just mentioned, you can see that the best performance achieved, let's say with 10% of the data, as you label 10% of the data points, is best for the USPS data set, which is about 90%, but it's below 80% for the speech data set and even lower for the text data set, right? So again, the point is if the graph signal variation is high, that means the task is more difficult. Okay, and when we get back to this in the context of neural networks, we will show that the neural networks actually change the feature space to make the graph signal variation smaller, right? To make it easier to classify. Okay, so we'll get back to that a bit later. Okay, so as a summary, these methods were not graph-based methods have been proposed before, and really the main novelty from a GSP perspective was the idea of the reconstruction with graph filters and the sampling or sampling set selection. Okay, so I'm going to spend a few minutes on a theoretical analysis of this idea before moving on to graph constructions. Okay, so the theoretical analysis assumes that we have the class indicator. This is the graph signal. There's a labels set and an unlabeled set, right? So this is the sampling set, and we have labeled points. And it assumes that we're estimating a cutoff frequency. This is for the reconstruction filter, and then the overall reconstruction minimizes the difference between interpolated labels and measured labels, subject to having a frequency that is below the cutoff frequency. Okay, so this is a little bit of an abstraction of what we just saw. This is the setup for this method, where we use an asymptotic technique. Okay, so we start with a model for the data. So let's say a distribution. We draw points from this distribution, and we assume the distribution is known, so we can draw an infinite number of points. And then we construct a distance-based similarity graph. And then we analyze the bandwidth for a particular class indicator. Okay, so and this is going to be asymptotic, so we'll have the distributions. When I show the experiments, we will see how do we do this. Okay, so we consider two different models. In the separable model is one where essentially the classification error is 0, right? So this is the distribution P of X. Points have more likelihood to be in these two regions, and there's a separation between two classes, S and S complement, right? And that separation is exact. So if you really knew exactly this boundary, the error would be 0. The second case is a non-separable model, where we have two classes that overlap in a region where there can be an error, right? And in both cases, we have the distribution. We can generate random data from the distribution, and we can analyze asymptotically the system. Okay, so as before, we have a similarity graph, right? So with the same weights as before, but one twist is that in the graph Laplacian, we divide by n, which is the number of samples, and that makes the things not blow up when you have asymptotically a large number of observations. Okay, so this is the graph Laplacian, and so now we look at this problem for both the separable and non-separable perspective. By estimating the bandwidth of this indicator function, right? So the indicator function tells me we're in class 1 or class 2, right? And so it will be constant for all the points in class 1, let's say +1, and it will be -1 for all the points in class 2. We estimate this bandwidth with this quantity, right, which takes the power of the Laplacian, and this can be shown to converge to the bandwidth of the signal, so basically the maximum frequency, and we consider this asymptotically. So we do several things to make this work. The number of data points increases asymptotically, but at the same time, sigma, which is this parameter that controls basically the local neighborhood, that goes to 0 as n goes to infinity, right? And so that's because otherwise you will have a very large number of points connected, right? So you increase the number of points, but you reduce the size of the neighborhood. So this is a shrinking neighborhood there. And as m goes to infinity, this as m goes to infinity, we also get a better estimate of the bandwidth. Okay, so the main result for both separable and non-separable models is that if we have a boundary, right? So delta S is the boundary between the two classes. The bandwidth of the indicator function converges to the maximum of probability along the boundary. Okay, and so the intuition behind this is pretty clear. If you take, let's say you have these two, the same distribution of points, right? So they have these two clusters, right? But you have a boundary that goes through here in this case versus here in this case, right? Now it's clear that this problem is easier than this problem, right? Because in this case, the boundary between the two classes goes through a low density point, an area where there are very few points, right? So the only points where you have an error will be points that are on either side of this boundary that are the opposite color of what they should be, right? And whereas here, your boundary goes through a region of very high density. So it becomes very difficult to separate the 2 points. Okay, so the basic idea is that if you have a separable model, the result is similar with the non-separable case. The bandwidth of the indicator function increases as the probability, the maximum of the probability density increases on that boundary, right? So for a given, for the boundary between the classes. Okay. So just to give you an idea of how we might use this, this is the PDF of the data in 2D that we use for an experiment, and then we combine the same distribution with different boundaries, right? So those would give us different configurations of data. And so, for example, we would have one boundary would be this, right? And so the separation between one class and the other goes directly through the center of mass, of, where you have the most density of the two for the 2 distributions. And another one would be this one, right? And so for each choice of a boundary between the distributions, you will have a different estimate of the supremum of the density in that boundary point, right? And therefore different classification performance or different difficulty in the classification. So several points. First of all, we can show that our estimates of bandwidth coincide with, our predicted bandwidth theoretically coincides with an empirical estimate of bandwidth, right? Where we generate the points, we construct the graph, and so on, right? So these are aligned. Also, these results are asymptotic, but we get reasonable approximations for values of n that are not so large. This is what we show here. And then with this method, we can estimate the label complexity, right? I mean, basically, the label complexity in this context would be if I tell you that I have n points and the bandwidth is some percentage of the maximum frequency, right? Then that percentage of the maximum frequency is the minimum number of points that I will have to observe to reconstruct, right? So for example, if I tell you that I have 1,000 points, but the maximum frequency, the maximum bandwidth is localized in 10% of the bottom 10% of the frequencies of the graph signals, then that would mean that I would have to observe 100 values and then reconstruct. And what we show here is that the reconstruction error, the red lines are predicted label complexity, and you can see that how the reconstruction error in these examples decreases also and goes to 0 after passing that estimated label complexity. All right, so let me move on. So in everything that I've described so far, we just used a graph construction that was essentially a k-nearest neighbor approach, or one of the methods that have been proposed in the literature. And now I'm going to talk about how we sort of revisited this problem and ask, what would be better for these problems. Okay, so going back to something that I presented in the beginning, we have first unstructured data, right? And what we end up with is either a graph or maybe a local neighborhood around each point, right? And so how do we do this? Now, I've made the case that this is useful in various cases, and both the graph construction and the local estimation are useful. Now, what the conventional approach is to define a similarity kernel, for example, the Gaussian kernel, and use either the k-nearest neighbor or an epsilon neighborhood, right? So essentially, you take a point, you compute the distances with all the other points, you define the k closest or those whose distance is below some level. The problem is how to choose this parameters k or epsilon, right? I mean, that becomes a parameter that will affect the result. And it's not very satisfying to have to compute these parameters empirically or try to see what works after choosing a parameter. Okay, so in our approach, we're reconsidering this problem as follows. We assume, again, we have a kernel function. Okay, so this could be the Gaussian kernel shown here, right? And so this is the negative exponential of the distance between the points squared divided by the parameter sigma. And we think of the problem from a dictionary perspective. We have one point that is the query, right? The point that we want to connect to others. And then we have the dictionary that has all the other points, right? Or maybe a subset of those other points. Okay. And so here what we would want to do is we want to find the sparse coding that represents this query, the current point, by a combination of the neighboring points. And we do this in reproducing kernel Hilbert space, where the kernel between 2 points xi and xj is viewed as the inner product between these functions in continuous space phi I and phi j. Okay. Now, when you frame the problem this way, you can have an interpretation of k-nearest neighbor as essentially a thresholding, right? In k-nearest neighbor, you compute all these values for all the points in your data set, right? And you choose those that are greater than some threshold, right? Or those that are smallest, that have the highest similarity. And so that means that essentially you're computing the k atoms with maximum inner product, and you set everything else to 0. Everything, all the other atoms you set to 0. Okay, and so can we do better on thresholding? So with this interpretation, k-nearest neighbor would correspond to thresholding. Okay, so our approach is to use techniques that are familiar for those of us in signal processing of various flavors of greedy pursuits, right? Where the key idea is that we may still identify the best candidates based on a residue, right? So the current approximation, and we find that the ones that has greater inner product with those in the approximation, but then we orthogonalize the error, right? So the method that we're really using here is some form of orthogonal matching pursuit where the weights of this approximation, right? So this is representing, we're representing the query as a linear combination of the neighbors, right? Plus some error. So in this approximation, the weights are computed so that this error is minimized, and that means that basically the error is orthogonal to the span of the neighbors that we chose. Okay, so basic idea: we form a local dictionary using KNN, right? So we still use KNN as a first step in this approximation, and then we perform one-stage orthogonal matching pursuits where the weights are chosen to orthogonalize the error. Okay, that's what we call the non-negative kernel regression construction, or NNK for short. Okay, this is maybe the most useful property that I want to highlight, because this NNK construction, if you view it from the perspective of a matching pursuits, it's orthogonalizing. It's selecting the weight so that the error is orthogonal to the atoms that you selected, right? So as in orthogonal matching pursuits. But this has a very interesting interpretation geometrically, right? And this is what we have. Let's say that node I is connected to a node J, right? Now we take these two nodes, we create a line that connects them, and then we have a hyperplane that is perpendicular to this line. So this orthogonality condition translates into saying that any nodes that are on this side of the hyperplane are not connected to I. Okay, and so that means that in the orthogonalization that I just described ends up producing a neighborhood that removes nodes that are geometrically redundant. And so, for example, if I connect this node to this node, then this hyperplane eliminates everything that is beyond. This hyperplane eliminates everything that is beyond, and so on, right? And when you do this, you end up with a polytope around each point. Now, the polytope doesn't need to be closed. It can be open on some side, right? But what this is doing is removing nodes that are redundant geometrically. Now, a qualitative comparison, this method, if you look at the k-nearest neighbor graph and you look at this central node and all the other nodes, basically the only parameter you have is k, right? And so if K increases, the number of connections increases. Okay. The closest method to what we've proposed is based on the local linear embeddings technique, which does pretty much the same idea, except that it operates in the linear space. So instead of looking at the kernel space with the inner product defined as the negative exponential of the distance, it tries to approximate the vectors directly, right? So xi is approximated, the vector xi is approximated as a linear combination of the neighbors. And NNK has this property of having a geometric interpretation. And so in this example, you can see that this node is connected to this node, but then nodes beyond that are not connected, right? So these nodes that are aligned are no longer connected. Okay. So what's interesting about this approach is it adapts to the local neighborhood. It selects points that are not redundant automatically, and it's much less dependent on initialization. In k-nearest neighbor, you could increase the k values arbitrarily, and then you will have a denser and denser graph. In this technique, even though you may increase k, you will not increase the size of the polytope, right? Once you've reached the correct value. Okay, so now for a little bit more quantitative performance, we go back to the label propagation problem, right? So remember, this is observing some points in a semi-supervised learning setting, and then doing a smooth filtering to interpolate at other locations. In this case, we use random sampling, so no optimized sampling, and we have multiple graph constructions. The three that are correspond to this idea are the matching pursuit, OMP, and NNK, right? So different. The only difference between OMP and NNK is OMP selects one point at a time, right? One neighbor at a time, and then selects the next one. Whereas in the NNK, as we typically implement it, starts with the k-nearest neighbor solution for k large enough, and then simplifies that with the orthogonalization. And so various observations. The first one is that the error is lower for this graph construction compared to all the other graph construction methods. Maybe also more interesting, when we look at different k, right? So we select a different set of neighbors. These techniques based on NK are much more stable. There's much less variation. And so there's less variation with respect to the sampling set. There's less variation when you initialize with different k's, right? And that means that we're sort of capturing the intrinsic geometry of the data, in a better way. All right, so I'll come back to this a bit later. Now I'm going to sort of bring these ideas to a deep neural networks and see how they can be used in that context. Okay, so now we're going to look at both some of the graph-based methods and also the graph constructions, and tie these to problems that are relevant for state-of-the-art machine learning systems. Okay, so I'll use as an example a deep neural network for image classification, and the test doesn't matter that much. But just to simplify, let's say we consider CFAR10. We have images that correspond to different classes: plane, car, bird, and so forth. And we have an architecture that has a series of convolutional layers, followed by pooling layers, and so on. So again, the architecture doesn't matter that much. Now, what we wanted to get at is to develop some understanding of how going through the layers modify the data set, right? Because you can look at the complete data set that you have at the beginning, and then you can run each of the images through the first layer, each of the images through the second layer, and so on, right? So basically, after each layer, you will have some representation of the complete data set. And we wanted to use that to understand how the system works. Okay, so this is a cartoon to explain the basic idea. So we have a supervised classification. Let's say that we have two classes, cats and dogs, and each of these points, each image is placed in a two-dimensional feature space, right? So of course, this is just for visualization. And so we have this image, and so forth. Now, once we are in some feature space, we can compute distances between 2 points, right? So we can compute in this very simple 2D embedding, we can compute the distance between this image and that image, right? And then we can construct a graph as we described earlier, right? We can look at the distance between nodes based on their embedding. We can decide how to sparsify the graph by k-nearest neighbor or some other technique. And so now you can see that maybe at the beginning of the classification, before the system gets fully trained, in this embedding, there will be cat images that are close to dog images. And so that means that when you construct this graph, there will be edges that connect two points that are in a different class, okay? And how would we know this? Well, one very simple way to figure this out is that we can choose for any embedding we have, right? After some layer, after some period of training, we can look at the label signal, right? Which would be +1 for dogs, -1 for cats in this example. And then we can see what is the graph signal variation, right? We can see how often we have values that are neighbors and have positive, that have different value. And so in this example, every red edge corresponds to a difference, right? It will be +1 signal for one image, -1 for the other image. And every green one would correspond to the same label. So +1 for both, -1 for both, okay? So our hypothesis was that if you look at the graph signal variation before training, and you compare that with the graph signal variation after training, it should change, right? Because training is redefining the feature space in a way that is favorable for classification. And so as a cartoon, this is what we were expecting to see, right? We were expecting to see that after training, somehow in the feature space, all the cats will be clustered together or the dogs will be clustered together, right? And there will be very weak connections between signals of different labels. And so in terms of graph signal variation, what this would mean is that the graph signal variation before training would be greater, so less smoothness, than after training, okay? So we set about trying to observe this, and we did some work several years ago, actually at ITA, where we consider M examples in each of the classes, right? Now we denote an intermediate representation for the ith example of class C at the output layer L and at the training epoch E, right? So basically we can collect all this data, right? We can run all of the images as we train, we can store their feature representations, and we can compute a similarity. It could be based on distance, we've seen this before. It could be cosine similarity, could be different things. And so what we would like to see is how does the graph signal variation before training compares to the graph signal variation after training. Okay, so here's an example. The x-axis is epochs. So this is the basically the steps in stages in training. This is the smoothness. So graph signal variation. So smaller means smooth, more smooth. And these are the layers. And so two observations. First of all, the distance between the layers increases as the training progresses. Second, you can see that the last layer, layer 7, has the greater smoothness, right? So it has the smallest value. So this cartoon that I presented here actually is what is happening in practice, right? The things are being separated, and you can quantify by how much based on smoothness. Okay, we took this one step further by comparing different networks on the different conditions, underfitting, normal, well-regularized, slight overfitting, extreme overfitting, and we see very different behavior. The example in the previous slide was a normal, well-regularized system, and you can see some spread between the smoothness of different layers. If the system is highly overfitted, you see that some layers have smoothness 0. So that means that essentially after sparsifying the graph, things are exactly separated. You never have connections between data points that are that have different values. We use this also again with Vincent Cripon's group to develop a couple of ideas. The first one was to enforce some kind of regularization of the training, where we constructed the graphs that successive layers, and we prevented the training from changing the graph too much. So you can think of this in, as having a constraint that prevents the gap in smoothness to increase too much from one layer to the next. We also did some work, again, with Vincent's group to replace the final layer from a cross-entropy method to a smoothness-based method, where we were using the graph signal variation as part of the loss function. Okay, so these were some of our early contributions here. Okay, now in what's left, I'm going to go back to the problem of graph construction and do the NNK construction, and see how we can use it also for these kinds of systems. And so as a bit of motivation, I think we're all aware of the fact that neural networks can often be trained to basically zero loss, right, for the training set, which doesn't necessarily mean that they will generalize well. Sometimes it can, sometimes it cannot. And this zero loss is often achieved by having in the final layer a pretty complex parametric classification boundary, right? And again, as a cartoon, if you look at a separation between these red and blue nodes, we like to think of a classification boundary that is fairly smooth, or it's a hyperplane, and it's nice and clean. But some of these classifiers in very high dimensional space with lots of parameters may, when you do something like this, well, you're achieving potentially zero error in the training set, but it's not clear that this generalizes. Okay, and so there's been some interest in considering local classifiers, and local in contrast to having a single partition, let's say a SVM with some parameters that can separate the classes, instead looking at points and deciding what label to apply given the neighbors. Okay, so that's what we've been interested in. And what we want to determine is what we can do with these local neighborhoods. Okay, so we proposed a local polytope interpolation using NNK. Remember that the NNK construction has this nice geometric property where a polytope is formed around each point. So we start by computing for each point a local set of neighbors, a polytope, and then we can use interpolation to define a classifier. So for example, we can look at this point, we look at its neighbors, we look at the labels of the neighbors, or more generally, we look at the membership function for each of the possible labels, and then we get an estimated label for this point. Okay, so a very simple classifier would be to take a node, look at the local neighbors using NNK, find the corresponding weights, and then select as a classifier the label that has the maximum interpolated value among all the possible labels. Okay, so how can this be useful? Well, we've used it in several ways that I'll explain next, but we've mostly used it as a leave one out estimation of classification error, and this can be used even though without any validation data. You can just look at every point, pretend that you don't know the label, right, and then interpolate the label from the neighbors, and then see what error you're making. And this is a local non-parametric approach, right? So it doesn't require an SVM hyperplane, for example, and we found it to be pretty robust. So I'm going to explain several ways in which we've used this. The first one is model selection without a validation set. Then I'll talk a little bit about explainability, and then I'll spend a bit more time on self-supervised model evaluation. Okay, so for model selection, what we're doing here is for the same data set that I described earlier, we have different settings for, to make it underparameterized, regularized, or overfit. And we're going to use this NNK leave one out classifier to learn about the, to predict the generalization from the system. Okay. So, okay, this is a result where we have underparameterized, regularized, and overfit. Okay. And then we have training and versus testing. Okay, so these are the results. Now, for generalization, what we would like is that the estimate of the loss function or the classification error with the training set, that should be reliable, right? We want to make sure that when we design it and then apply it to to data that was unseen, it is reliable. So let me focus your attention on this case. This is the overfit scenario, right? And you can see that in the overfit scenario, the error from the model, right? So this is the error that is estimated in training, the error in the training set becomes very small, right? So in other cases, it may be even zero. Now, when you look at the NNK construction and the leave one out cross validation, okay, so there what we're doing is for every point in the training set, we look at the neighbors and we estimate the predicted label from the neighbors, compare that to the true label, right? And that's the error. And we can see that the error from this linear local interpolation is higher than the model. However, when you look to the test data, it actually turns out that the error from the model is higher, whereas the error from the NNK leave one out interpolator is better. So by having this local interpolation technique, we have a better prediction of generalization, right? So even though we may have a model that at high dimension with an SVM classifier may tell us the error will be arbitrarily small, we can see that in reality, it will not be that small, okay? We can also use the NNK construction to give us information about some solutions because it gives us information about images that are nearby, right? And so as an example, we can explain local solutions. In the examples in this slide and the next one, what we have is the point, the image at the left is the query, right? So that's the point that we consider to construct the local neighborhood, and the images on the right are all the neighbors that were found by NNK. Okay, and so in examples like these are examples from CIFAR 10. You can see that there are duplicates, right, in the data set. They're really identical images or images with very little difference. You can also see cases where you have errors. And so let me move on to the next one. If you look at the leave one out predictions, right, and you look for points where you have a big error, you can go and analyze locally what's happening. And so in this example, you have a horse, actually a dog, and horses, you have a bird in planes, right? So this local estimation allows us to determine what's happening locally at this level, right? So summarizing, the local interpolation allows us to first understand what's happening, what are the neighbors that are more relevant, which ones are connected. This we can do at any level of the deep network, and also it provides a more robust estimation of the error in the testing set. Okay. All right. So now to conclude, I'm going to talk about our more recent work, still unpublished, on analyzing the geometry of deep learning. And we've been considering the case of self-supervised learning, where we may have models that are learned through some source data set and with augmentations. I'll say more about self-supervised learning soon. But we're interested in the transfer learning scenario where we have a source represented by this manifold and a target. And we would like to understand which models to use for a particular task, what augmentations, and it's in general difficult because we're comparing things that are not very easily comparable. They have the dimensions of the features are different. The models include different design choices. So one thing that we're exploring is how an NNK construction can help us understand the local geometry of the data. So as an example, the intrinsic dimension, since the NNK neighborhood does not increase arbitrarily in number of neighbors as k increases, right? Because neighbors that are geometrically redundant are not added, then we think that the intrinsic dimension of the manifold can be estimated based on the number of NNK neighbors. If we want to look at equivariance, we can think of the NNK polytope diameter. So if you take a data point and augmentations of a certain type, if they're all very close in the feature space, that means that the feature space doesn't, is invariant to those augmentations. But if they're very far in feature space, then we will see that the opposite is true. And so these are some of the measures that we're considering. Now, applying this specifically to self-supervised learning. In self-supervised learning, you take data points plus their augmentations, and you train a model that forces the augmentations to be close to the original data point. And in practice, you use the encoder, so an early stage of that model instead of the final stage of that model. Okay, so I'll describe an experiment where what we did was to feed ImageNet images and rotated versions, right? So one image plus rotated versions. So those are the augmentations. We obtained the NNK neighbors in feature space, right? And so this is after a system that semi-supervised learning system that has been trained, and we measured the NNK polytope diameter. Okay, so the polytope diameter we estimated as the maximum distance among the set of neighbors of a particular point, right? So that's an estimate, and this is in the range 0 to 2. So as I just mentioned, let's say that you have a system where that is very invariant to rotation, right? So if I'm invariant to rotation, then I think all of these points are the same. And therefore, what will happen is that the feature representation of all of these points will be very close to that of the original. But if the system is not invariant to rotation, these are really very different images, right? And then the distance would be larger. And so what we expect to see is that if the diameter is large, the system is equivariant. So these changes do not affect these changes maintain the augmentations are at a high distance from the input, but if the system is invariant, we expect the diameter of the polytope to be small. Okay, so this is an illustration of this idea. Each of these points corresponds to a different self-supervised learning methodology on ImageNet. This is rotation equivariance, and this is the polytope diameter, right? So basically, when the equivariance increases, that means that the system is preserves the distances better, right? And this is the accuracy for two tasks, right? So the first task requires invariance, right? It would be, think of it as an image classification task where you want to find one image and identify that it's a cat or a dog and so on. Okay, and what we can see is that the more invariant it is, so the higher it is, you have the more the better classification, right? So in this direction, more invariant; that direction, less invariant. Okay. Now the second task is actually finding the normal direction to a surface, right? And so the normal direction itself, it depends on the orientation of the object, right? And so here we have the opposite behavior, that the accuracy is higher when the invariance is lower. Okay. And this is work in progress, but this gives you an idea how this tool for analyzing what's happening locally can help us understand what models work better for particular tasks. Okay, so let me conclude. I think I'm just slightly over time. Summary here, the main takeaways is we use graphs as a way to analyze machine learning systems. Specific interest that we've developed here is to build similarity graphs. And ideas that we've addressed: what to label, how much to label. So in the semi-supervised learning setting, we've studied in depth how to form a similarity graph, and I think we have methods that are have advantages over previous techniques. And a lot of the ongoing work has to do with a geometric analysis of deep networks, determining how to train them, how interpretable they are, estimating their generalization performance, and more recently, we've been looking at self-supervised learning. And just to leave this here as a last slide, for the graph signal processing part of this, there's a lot of ongoing work and some overview papers, and in particular, I recommend several special issues of Signal Processing magazine that go in depth into some of the topics. There are a couple of textbooks, including the one I finally finished, which I think will be available, in fact, this month. So yeah, that's and there's a lot of code available and several toolboxes. So let me stop here, and I think if appropriate, can answer any questions you may have. Thank you.
Thank you, Antonio, for this very clear and interesting talk. There are already a few questions in the chat, so maybe we can start from those before giving the floor to other people.
Okay. So how do we want to do this? I look at the chat. Okay, so going in order. So in feature space, the nodes have locations that are vectors, and the labels can be scalars, one per node, or can be vectors, or there could be several vectors, like several indicator functions. Right. So in the construction of the cumulative energy, the data sets in those three cases that I showed, the graphs were constructed in the original domain, so there was no feature extraction performed. And these were constructed with the same techniques that people in the field have used, right? So either cosine similarity or distance-based similarity. And I guess the slide where I have those details is this one, and these were essentially methods that people in the field had used. So we didn't really these were KNN, and we chose what other people had chosen. So is it possible to improve the GSV complexity of the task by optimizing the graph constructed? So I think that we focus mostly on improving on how the training of a neural network improves the GSV of the task, right? I think the graph construction itself affects the result. Clearly, if you have KNN and you increase K, you end up having, higher variation, right? Because you have more connections. But we've been mostly focusing on using the graph to understand the geometry of the data rather than, changing the variation. Of course, if you have a task where you're trying to interpolate data from labels, you need to use a good graph, and in that context, it will be useful, right? But yeah, we've used it mostly to visualize multiple choices. So in the NNK results that we showed, I think we were using either cosine similarity or the Gaussian similarity, but one of the two. The NNK idea works as long as you have a kernel function with values between 0 and 1. So both cosine similarity and NNK, I mean the distance-based Gaussian similarity would work. So it depends on what is used in these cases. So in the example here, two of the examples use the distance-based Gaussian similarity, and the other uses the cosine similarity. Okay. Yeah, so good question about the Delaunay triangulation. We've investigated that. I think it's but it came up in discussions, and I think the short answer is I don't know. It may have something to do, but we haven't really explored that in depth. But yeah, that's an excellent question. And so we normalized versus combinatorial Laplacian. We've used both. It depends on the application, and of course, if you use a normalized Laplacian, that means that there will be a difference in the actual variation that you compute. Is it true? The number of nodes. So I'm not sure about graph classification. In our case, we're not really classifying graphs. We're so most of the examples that we've shown in the latter part of the talk, that I showed in the latter part of the talk, are examples with images, right? So we're not. This is not about graph convolutional networks or graph classification. We're using the graphs to understand the data sets, right? And we're working with images. So I don't know. Are there any other questions?
Maybe if there are other questions, you can also unmute yourself. There is already one in the chat. So Antonio, maybe the last question in the chat is related regarding the NNK assumption on modeling the geometry of the data.
Right. So that's also an excellent question. I think that so it doesn't require it, right? I mean, we can run NNK whether the data is on a smooth manifold or not, right? So I would turn the question around and basically say that if there is a smooth manifold underlying the data, then we would observe certain things. And one thing that we've observed in various instances is that when you initialize the graph construction with KNN and you let K increase, then let's say you have the K for KNN and then the K, let's say K hat for NNK. What we observe is something like that. Right, that as you increase the KNN, K and KNN, right, you increase the size of the dictionary, so to speak. The number of nodes that you actually connect does not increase at the same rate, right? So it saturates, and we think that that's an indication that the intrinsic dimension of the data is low. Now, how low is the intrinsic dimension depends on the feature space that you choose, depends on the complexity of the task. So we can use all of these things regardless of whether there's a smooth manifold or not. But if there is a smooth manifold, then we will expect to see some of these behaviors, right? So it's more, I look at the NNK construction as more of a lens with which to look at these very complex high-dimensional systems. And if there is smoothness, then we would see that. So the GSV of a particular graph have the same interpretation for another graph. I mean, each graph is different. I think the question is, do you have the same data set or not, right? So if you have, let's say, the same data set, the same points as a starting point to construct the graph, and you change the graph construction a little bit, right? Of course, there will be some relation. It will be some, let's say, the comparison between KNN and NNK. The way the GSVs will be different, although they will represent the same data. If you have different subsets of data from the same overall data set, I think everything would be can be different. I mean, you might expect that if you do a sampling of points in the data set and you have enough samples, the GSV values would be similar, right? That you might expect, but they don't need to be the same. So basically, I think the most expensive part of the graph construction is the KNN part, right? So for the KNN part, we can use existing methods that are fast for KNN, and then once you get to once you found the initial KNN neighborhood, the extra work needed for NK is not as much, right? Because then it's a function of the number of nodes and the size of the neighborhood. So it's n times k. But the initial step, we can leverage any techniques that people have used for fast KNN. And I should say it's not here, but we have both MATLAB and Python code on GitHub. Maybe I should have included that for the KNN construction. And so if you go to Sarath's webpage, I'm sure you can find that in our group webpage. We also have pointers to this, and you can always email me if you would like the pointer.
Thanks, Antonio. Is there any other question from the audience? Maybe I can ask a last one. So have you tried to generalize or to see if this analysis related to the smoothness over the layers of a neural net, does it generalize also to graph neural nets?
We haven't looked at that. And to the extent that graph neural networks, you still have some kind of embedding for each object, right? So each graph, is embedded into some position and feature space. I think it might be possible, but we haven't looked into that. Okay. And the methods that, and I'm referring, I think the easiest extensions will be to scenarios where we have sort of discrete objects, right, that we want to classify, right? So, a graph to be classified. I think extending this to applications of graph neural networks in, I don't know, label propagation, things like that, where you have a large graph and you try to propagate the labels there, that would not be so clear. So yeah, I mean, I have to acknowledge a lot of this is dependent on having, I mean, a lot of the experiments are based on image classification tasks, those kinds of things.
Okay, thanks. Any other last question for Antonio? It seems not. So thanks, Antonio, again for this very nice talk.
Thank you very much.
Thanks everyone for joining today. Have a nice day, evening, afternoon, depending where you are.